Thank you. Okay, so today I will switch to time reversible systems. Wave equation, which is a subject of Professor Deman's talk, makes part of this. I will not speak very much of that. In fact, I will use the existing results for the wave equation to derive new results for dispersive type equations, which are the equations typically of Schrödinger type or of Kirchhoff time for elastic plates. Moreover, I will adopt an approach inspired from finite dimensional system theory, which is based on Hautus type conditions, which allow, firstly, to pass from results for the wave equations, for instance, to results to the Schrödinger equations, and also to establish, in fact, new results for Schrödinger equations in an independent and very elegant and elementary manner. So this is the plan. I will remind some background on observability. So my viewpoint will be the dual one. Essentially today I will speak about observability, but we have seen the duality between exact observability and exact controllability. I will explain then how we pass from the wave to Schrödinger equation. And finally, I will go to frequency domain tests for second order in time equations and for the perturbations with application to the equations of elastic plates, which will be linear or non-linear as a von Karman system. So, the control systems I will speak about essentially are either exactly sigma plate or sigma Schröd, which appear here, or some perturbation of them. So what is sigma plate? It's the equation of a Kirchhoff plate controlled on an internal subset and with the boundary conditions which are called hinged, which are not the most realistic ones, but are the ones which mathematicians prefer, because our operator, when we write this in operator form, will be the square of the Dirichlet Laplacian. And of the Schrödinger equation with a control which acts again inside the domain. What is known about these systems? That they are exactly controllable in arbitrarily small time, provided that one of the following two assumptions is satisfied. Firstly, the corresponding wave equation is exactly controllable in some time. So you can take this as an assumption. I don't care how it has been established that the wave equation is controllable. In some time, of course, it cannot be arbitrarily small. Then automatically, we have a simple argument which I will explain, gives you for free, with the functional analytic argument, that the same holds for the Schrödinger and the plate equation. And the second case is when omega is a rectangle, and O is anything, in fact. O can be a set of positive measure. Needs not even to be an open set, but so it can be very small. So this second result is not true. So with very small observation domain is not true in general. It's very much dependent on the geometry. Okay, so I said I will take this as an assumption that this one is controllable. So when this is true, so my colleague will explain you with all the details already did, in fact, is when the control region satisfies the geometric optics condition, roughly speaking. So there are some very small, let's say, points where we have to be careful, but essentially it's a necessary and sufficient condition. So I can replace for smooth domains this assumption by the Bardos-Lebon-Roche condition. if I'm speaking about wave equation. But somehow I will again present my results in a more abstract manner, and we will look. So what about perturbations? So as I mentioned, I will be interested in perturbation of these two systems, plate and system, and Schrödinger. Let us begin with Schrödinger. It's easier to understand, and easier, the equation is shorter somehow. Huh? So I begin with Schrödinger, and I add a zero order term. This system, I want to look to it in L2. I take it, let's say, L infinity, in a way that this perturbation operator will be a bounded one in the state space L2. And the question is, under which circumstances the fact that the initial system was controllable implies that the perturbed one is also exactly controllable. So, in fact, there is not such a result. Such result in general does not exist. What can we say? It is easy. It's folklore. In fact, I will in fact prove somehow this folklore a bit later. That if the wave equation is controllable from O, then the perturbed system is controllable. But saying that the wave is controllable from O, it's a stronger assumption than saying that Schrödinger is controllable from O. So this is a very simple proof. This is the fact that this, with this strong assumption, is very easy. When omega is a rectangle, the situation is better finally. O can be any domain and we have controllability, but this has not been treated as a perturbation of the Schrödinger equation. It has been redone from scratch in a series of papers of Burke and Swarsky and Bourgain, Burke and Swarsky, which are extremely sophisticated. So adding here a zero order term for omega a rectangle and O an arbitrary set of positive measure yields exactly controllable system, but with extremely sophisticated techniques. What about the plate? For the plate, all what was at least possible to find in the literature was that you can perturb that an operator up to order 1, which means that in fact by compact operator, when I'm in the state space, a differential operator of order 1 will be compact in the state space, which is essentially H2 times L2. And then this is a classical, more or less classical compactness uniqueness approach. Okay, so this is a state of the art according to perturbations. What are our new results? So, in fact, our really new results concern only the plate case, obtained in a paper with Megan Bournissou and Sylvain Hervé-Dozat, is that I allow second order perturbations for the plate with some, this is a kind of making my operator, condition making my operator skew adjoint, because I did not write it as self-adjoint, sorry. I didn't write it in divergence form, okay? So this condition red here is just to have it symmetric from H2 to L2. Again, if I assume that the waves are controllable, so assumption stronger than saying that the plates are controllable, then the perturbed plates will be controllable. That's what we're saying here. So what's a bit different of the case of Schrödinger is that our operator now will no longer be skew adjoint when I write the perturbed operator, when I write all this in first order form, will no longer be skew adjoint, which let's say requires a special attention, since the results I will apply soon are essentially valid for skew adjoint generators. So that's where we want to go, essentially. But in the meantime, I will show you a lot of things, hopefully interesting about from the methodological viewpoint. And we have also a second main result, which is on a system where I have worked, let's say, more than 30 years ago, and now I'm coming back, which is the von Karman plate system. So it's the simplest non-linear model for elastic plates. So this is the equation. Here you recognize the Euler-Bernoulli or Kirchhoff operator, and there is a nonlinearity which is cubic and non-local. So here you have the formula for the bracket, which appears here, and phi of VW is the solution of this stationary B-Laplacian problem. It's called the Airy stressed function. So it's a nonlinear model, which is very beautiful, and because this nonlinearity, if you take W to be in H2, this nonlinearity will not be in L2, but will be very close to be in L2. So this is a system for which, for instance, Tataro developed very beautiful compactness, compensating compactness methods to show that it is well posed. Because there is some epsilon which seems to let's say, to be absent, so to miss, but in fact, this epsilon is there and you recover it by compensating compactness. But I will not go into this. I will in fact use this implicitly. In the proof we use it, but for the moment we will forget about it. So what was known about this one? So well-posedness, it's already not completely trivial. And but from well-posedness, it's not difficult to get local controllability around the zero state, around the stationary state W equal to 0. What we are doing is that the system is locally exactly controllable around any stationary state. So that's the novelty we bring in due to our linear perturbation result, in fact, and in fact, and to a fixed point procedure. So these are the main results which are new, I would say. Now let me go back to the background part. So we spoke a lot about the admissible control operators. There is a dual notion, admissible observation operators. So here it's somehow much simpler to explain. I have an evolution equation with a generator A, and I have an output C, with C also unbounded. C is defined a priori only on the domain of A, not on all the space X. And then I'm saying that the system is this is an admissible observation operator for the semigroup if I have this inequality for Z0 in DFA, which what means? It means that the operator which to Z0 associates the observation can be extended to an operator from X to L2 of 0 infinity Y. But this inequality is good enough for us. It's somehow I don't need to write too many operators when I speak about observation. Then we have several types of, as we had several types of controllability, we have the dual notions, several types of observability. Exact observability means that from the observation in time tau, you can recover completely the initial state in X. Approximate observability means that if your output or observation is 0, then the initial state is 0. And final state observability, this is the dual of null controllability, means that from the output, you recover the final state of your system. And this is equivalent to null controllability. I'll write the result a bit later. Again, if X is equal to Cn, these three concepts will coincide and will be time independent. Now, do we know something in an abstract setting about perturbation of exactly observable system? There is only a simple result. So there is a very simple result of Had, which he wrote formally in the first, which says that if I perturb the generator by a small bounded operator, then exact observability will be preserved. And there is a second result due to Duprez and Olive, who formalized very well-known things going back to Bardos, Lebeau, and Roche, which says that exact observability is preserved, provided that the perturbation of the generator is a compact operator, so more than bounded. And I have this is called a Hautus type condition. You'll see why. So the kernel of this operator is the trivial one, whatever the complex number S is. So it means that I don't have, roughly speaking, unobservable eigenvalues, eigenfunctions for the perturbed system. Now, this duality, observability, controllability, I mentioned it already yesterday. It is based on that theorem of Douglas from 1966, but in the context, a system theory has been written explicitly by Dolecki and Russell in 1973, and then baptized Hume much later. This says that the pair AC is exactly observable if and only if A star C star is exactly controllable. And I remind here the definition of this fact. We have seen this yesterday in detail, but we are looking in the other sense. No? Now, how can I prove that a system is, or pair AC is observable? In finite dimensions, there is the famous test of Carleman, which has not many good generalizations in infinite dimension. There is another test in finite dimension which has been obtained practically at the same time, and it's the Hautus test, which says that a pair AC with AC matrices is observable if and only if the rank of the matrix Si minus AC, so I just juxtapose them, is equal to n is full for every complex number. And I see that here, in fact, the only the only case when it risks to be not full is when S is an eigenvalue. No? Because if S is not an eigenvalue, just Si minus A will have rank n. So this is why it is equivalent to the fact that the eigenvectors are observable in finite dimension. And by a simple compactness argument, the first condition is equivalent to this one. In finite dimensions, nobody will write it like this. As I wrote it here, passing for equivalence between these two ones, first and second, is just due to the compactness of the unit ball in Rn. So nobody will write it like this in finite dimensions, but this is a way which can be used to generalize the assertion to infinite dimensional space. Now, what about infinite dimensional case? There is no such necessary sufficient condition as in finite dimension. There are the first work on the infinite dimensional case is due to Russell and Weiss, which gave some necessary condition, which is not in general the path which is interesting us when we do PDE control. And the first sufficient condition, which is quite general, is due to Miller, which says that if my operator is Q adjoint, in other words, this is hidden in the fact that T is a group of unitary operators, and by Stone theorem, these two facts are equivalent, then exact observability is equivalent to the existence of two constants, capital M and small m, such that this inequality holds. Okay? Again, if I take I omega to be an eigenvalue of Z0, this implies that, but this is a very particular consequence, that the eigenvectors are exactly observable. But this is not sufficient in infinite dimension. So this, the interaction of these two terms is much more subtle. And if the above estimate holds, the controllability time is larger than m pi. This last information is not sharp. So even if you take the 1D wave equation with boundary control, apply this test, you will not get the sharp controllability term. But that's not the most important thing in this approach. This is the result of Miller. Now there is a slight generalization which we formalized in our book with George Weiss, which says that in fact it suffices to have this inequality in the space E alpha, which is a space of high frequency. So these are the frequencies larger than alpha, because I have here an orthogonal, and to have observability of every eigenvector. Here, everywhere, I will suppose that A has compact resolvent, so discrete spectrum, okay? So I reduce the problem to the same estimate, which doesn't affect the controllability time only in high frequencies, and I add the condition of observability of all the eigenvectors. A priori, it should be only the one from the low frequency, but since I want to play with this frequency, I put the assumptions forward. There is another way, a second way to formulate this test. Is what's called a spectral test, which is based on the construction of wave packages. So I take, given a real number, real omega, and a positive number r, I define the set of indexes which give my basis of eigenfunctions, such that mu k minus omega is smaller than r. So I take, so here a number omega, here omega minus r, omega plus r, and I'm looking to all the lambda k's which are in this interval. So this is called every combination of eigenvectors which corresponds to this lambda k is called a wave package, the wave package associated to omega and r. So the following statements are equivalent. I have observability of these wave packages uniformly with respect to omega. So here r is fixed, but uniformly with respect to omega. And the exact observability, again, in some time, the time obtained is, again, not sharp with this methodology, but we obtain a time. So this one, for instance, would, again, this one, it suffices to check it in high frequencies. This one gives immediately, for instance, the controllability when, for one-dimensional system when you have a gap, because your wave package, provided that you choose R small enough, will be formed by one eigenfunction. If I have the 1D property, essentially 1D property, lambda k plus 1 minus lambda k larger than delta larger than 0, then my wave package and R small enough, my J of omega R has one element, at most one element. So the problem is immediately reduced to the observability of eigenfunctions, which again in simple one-dimensional case is a trivial question. But that's not why we develop this test, because anyhow, even in 1D, with this kind of tests, you lose the optimal controllability time. So this is not, but it's a one-line proof once you accept this, but without giving the sharp time. What do you know about? Let me now come back to the Schrödinger equation and remind the result of Jafar, essentially, which in a rectangle. Why? Because I want to give you a proof which I like a lot, which is extremely elementary, and which is due to Zygmunt. He didn't do controllability, but nevertheless, he proved exactly the inequality which we need. So what does the Jafar result says? With an open set in his case, but arbitrary, and omega a square, a rectangle. We can put easily a rectangle, but we will give the proof for a square. We have controllability in arbitrarily small time for any open control domain O. Then there is the work of Burgen-Zworsky, which add perturbation and also allowed O to be a set of positive measure, not necessarily an open set. For the dual problem, what we have to show is this inequality. As here something is, I will apply my spectral test. To establish the, which is the dual problem. The dual problem will be phi dot minus I, so let me change sign here. Phi dot is equal, well, up to a sign, which doesn't matter here, is equal to I Laplacian phi. Phi on the boundary is equal to Laplacian phi on the boundary is equal to 0. And what I want to prove, so I want to prove that this system is observable. Sorry? Yes, it's not the plate. I'm anticipating. Thank you. Only phi on the boundary, but if phi is 0, phi dot is 0, and Laplace phi is 0. No. It's true. Okay, which are here my eigenvalues will be lambda mn is equal to m2 plus n2. Sums of square, in particular, will be integers. And the corresponding eigenfunction will be phi mn of xy is equal to sine mx sine ny. So what do I have to prove according to the spectral test? I choose r, small r, smaller than 1, which means that in a package, the package are defined by m2 plus n2. Instead of omega, I will put a capital R here. So a package, I can immediately draw the eigen values corresponding to a package will be lattice points, so it means of integer coordinates, on a circle of radius r. So these are the lambda mn from a package, provided that I choose r, small r, larger than 1, smaller than 1. Oh, because this is the definition of mu k minus omega smaller than 1. Okay, and then the inequality to prove will be exactly this one, with instead of exponential sinus. But of course, if I am able to prove this one, I'm able to prove the other one also. So that's what we, if we prove this, we obtain controllability, observability in some time. We will not obtain the sharp result. But let us do the proof of this because it's very beautiful and nothing to do even with the proof of Jafar, which is beautiful but is difficult, or the proof of Burgen-Zworsky, which is more than difficult. So here you will see I will do everything with these laws. However, something which is better than in Jafar is that O will be allowed to be a set of positive measure. Let me give in detail the proof of Zygmunt. First, so this he published this in the proceedings of the ICM from 1972. This was his contribution to the ICM. So first, a very elementary lemma. I take the Fourier transform So here it should be Dixi, which is missing. And here I take the Fourier transform so here nu is in R2, and I take the Fourier transform of the characteristic function of O. And then this lemma, which should be very well known, but he proves it, says that for every nu different of 0, the value of this Fourier transform is smaller than, here I will change the notation from now on, I will not use mu of O, but it's the measure of O minus epsilon for some strictly positive epsilon. And in fact, the proof is extremely simple. By Riemann-Lebesgue, this goes to 0. So when nu goes to, when the modulus of nu goes to infinity, and then I have just to prove that it is not equal to the measure of O. In other words, that this is not always of modulus 1. Or it cannot be, because it would be only if this would be equal to 0 modulo 2 pi all the time. And if it holds, it's very easy to see that this would signify that, in fact, the set E is of measures there. It's a finite number of hyperplanes. Not finite, countable number of hyperplanes, which is enough to say that it cannot be true. And this one is the best. If I have free lattice point on the circle of radius r, it's a poorly 2D proof. I have this inequality. Where does it come from? So I have 3 points, lambda, mu, nu. I have a triangle. The 3 lengths which appear there are the lengths of the triangle. And I have a famous formula, R is equal to ABC over 4S in elementary geometry, where S is the area of the rectangle. So it's the first time I use this in control theory. And then you are done, because S, these points are lattice points. You write the formula with the determinant of the area, and you have S larger than 1/2, because my points have integer coordinates. It's very easy to see. You just write the determinant, and you are done. You obtain this very beautiful inequality. We'll see immediately how we use it. And now I take the quantity for which I want to find a lower bound. And here the procedure is quite inspiring. It has common points with those used to prove Ingham typing inequalities, for instance. But it's much simpler than Ingham. So what I do, I develop. I will have diagonal terms, and those diagonal terms, so I write here, I denote by lambda, mu, and nu the couples of type Mn. I have the couples with, where I have here with plus and with minus, the same thing. They give me this diagonal term, no? There is, as usual in this kind of sums, I have a diagonal terms, okay? And then I have all the others. Okay. So it's the sum of this term and its conjugate. All these terms give me this, no? When I do, and these are all the others. And why key appears? Because I have exponential of, maybe there is a minus here, which I forgot. Doesn't really matter. And that one, that one appears because when I take the conjugate, there is also a minus, and I have a Fourier transform of the difference of key evaluated in nu minus mu. So that's why the order is nu minus mu. Yeah. Okay, so what's the principle, which is very classical, is to say that I want just to prove that the diagonal terms dominate the non-diagonal ones, because at the end, I want to have a constant times the sum of the diagonal ones. So what is Zygmunt doing? First, by Parseval, I have that if R0 is large enough, this sum is arbitrarily small. No? Just, this is Parseval. And so he just puts very carefully the epsilons, and he chooses R0 to have this. We don't know why, but it's possible, clearly. And then we call delta the set of all the possible lengths. Is the lengths or is just a set of differences? I think that here it should not be, now here there are no bars. The set of all the differences of two multi-indexes lambda minus mu, where lambda and mu are on the circles, like here. So it's the set of all the differences, not of the absolute value of the modulus of the differences. So delta, and then we split this into those where here the modulus appears is smaller than R0, and the other ones where it will be larger than R0. That's okay. We'll see now. And then we correspondingly split this sum this sum here in a sum which corresponds to delta prime, called Q prime, and the sum which corresponds to delta second, called Q second. What about Q second? This is easy to evaluate. So here the sums are double sums. Attention, and the sums here, I don't write the indexes, but it's the sum over, it's in Q second. Lambda and mu are on the circle, are lattice points, and the lambda minus mu is larger than R0, because I am in Q second. Okay. But so now this double sum, I will transform it in a simple sum in which way? I will sum according to the values of nu minus mu. And on a disk, on a circle, what's mean here very deep result, I can have only two chords having a given length and a given direction. Oh? So if, for instance, I want chords which are vertical and which have a given length, I will find only two, like this, which are symmetric, Oh? And this is why, in fact, when I sum according to this summation index, I will have only for each value of nu minus mu, I will have only two possible choices for mu and nu. So this is why here this will reduce, gives exactly what I'm writing here by Cauchy-Schwarz, and then I use my assumption on R0, and I obtain that all this is smaller than epsilon over 2. That's where the assumption on R0 matters. I obtain that this is smaller than epsilon over 2, the sum over all the lattice points of C nu squared. So I have a bound for Q second. Now I fix R0 is fixed with the bound properties, and I choose R large enough in order to be able to split the points, lattice points on the circle into distinct pairs having this property. So what does this mean? That if I have I have an R0 which has nothing to do with R. The R can be much larger than R0. And according to lemma 2, if I have 2-point close, I cannot have a third one. So if lambda is close to mu, lambda cannot be close to another one. This is clearly due to lemma 2. It's very easy to close. So my points, in fact, I have again a double sum, but this sum will be splitted in a simple sum formed by just with general term of this form. Oh, what did I do? I went in the other sense. And this general term, it's easy to bound. I just apply Cauchy-Schwarz, and then I use lemma 1. I use lemma 1 for the Fourier transform of the characteristic function. And so I have shown that Q prime is smaller than the measure of O minus epsilon, sum of sinus squared. And I'm done. And I'm done. Let us look again. I have a coefficient O here. And from that one, I subtract something with O minus epsilon. I have also, of course, the other one, but I still keep an epsilon over 2. This was the point. So I keep an epsilon over 2, so I have my observability inequality. So this is one of the really most beautiful proof I have seen. And it gives a result far of being trivial. Now there is much more done on Schrödinger equation. So in fact, on Schrödinger equation with internal of boundary observation, when we do boundary observation, things are more complicated. So for instance, in a square or in a rectangle, we have showed in a paper with Gerald Tenenbaum that I can observe on an arbitrary small part of the boundary, but this is far, far more complicated. It mixes number theory, Kahne's theory of non-harmonic Fourier series, and so on. Then there are those results of Bourguin, Sursi, and of Anantamaram and Leoto, which investigate more complicated geometries and perturbations. So here I wanted just to show how we attack directly using, but however, using Hautus test, the problem of exact observability of a Schrödinger type equation. We can do the same for the plates. It's very easy to, in fact, we can deduce the result for the plates from this one very easily. Now I will go back and explain how, what I mentioned, how I go from wave to Schrödinger. So here I will avoid the difficult analysis because I will assume I know what happens with the wave equation. So here I repeat the known result of Bardos-Roche for the boundary observation case. And I'll go to two notations which allow me to formulate it in an abstract manner, which is very useful. So this is why I didn't denote Sobolev spaces by H, because H will be an abstract Hilbert space. I have a positive operator with compact resolvents. I denote by H1 half the usual space, domain of the square root. And I can define, in fact, all scale H alpha using eigenfunctions and eigenvectors. It's classical. And I take several observation operators. So I take an observatory C1, which goes from H1 to Y. And I define C, which goes from X1 to Y by C1 and 0 on the second component. So in other words, I will, for a second order system, I will absorb the first component. We'll see immediately. So what is this abstract passage? Very important, the operators. So in fact, so the equations I will consider, the systems I will consider, maybe it's much easier to write it like this, will be for Schrödinger, Z dot is equal to I A0 Z, with the observation Y is equal to C1 Z. So that's, let's say, the target system, the one I want to prove it is observable, and the one I will assume it is observable is W double dot plus A0W is equal to 0, and with the output C1W. So that's the one I will assume to be observable, and that's the one I will obtain that it is observable. And more precisely, this theorem says if AC is exactly observable, so this one, in some time, then A0C1, so the first one, is also exactly observable, but in arbitrarily small time. Even if for the other one, I have no information on the time. And that's not difficult. I just apply the Hautus test. I put instead of omega, I put square root of omega for the wave equation. So I write this as a first order system with this operator, no? As usually when I'm dealing with a wave equation. I write the Hautus test because I know it's necessary and sufficient. I use here the necessity. I have this inequality for some constants, capital M and small m. Then instead of Z tilde, which is something in the product space, no, I take this couple with Z in technically in DFA0 free half, and then after a very elementary calculation, this is what I get, which is practically the Hautus test for the Schrödinger type system. But with a big advantage, I have an 1 over omega here. So the constant which gives the time can be done arbitrarily small, provided that omega is large. And indeed, I can limit myself to large omega because I have unique, I have observability of eigenfunctions, eigenvectors, of eigenvectors. Yes, I have it because waves are controllable. This is supposed. So I have all what I need with a constant you see here before this term, arbitrarily small, which means when my control time is arbitrarily small. So more generally, this conclusion would be the same if here I have any function of omega which goes to 0 when omega goes to infinity. That's all what I know. And this, so here in fact what I have proved, it's maybe to what it should be retained, is that if Hautus with some constants holds for wave, then it holds for Schrödinger, but with a coefficient here which goes to 0. That's the important information. And so we obtain this result, for instance, if the path of the boundary satisfies the geometric optics condition, or in other words, wave equation is controllable, observable, then I have this inequality for Schrödinger in arbitrarily small time. And that's for free. So what's for free? So what's interesting is that Gilles Lebeau wrote a paper on that, and where he redid almost all of the microlocal approach, probably because for him it was not difficult, but for most of the people, you don't need to redo it in this case. With this assumption, you need strictly nothing more. When you know it holds for waves, it holds for Schrödinger with this observation. So this has been remarked already by Burke and Zwosker, made precise and in this abstract setting by Luc Miller and myself. So this means in particular that means that in particular here I can perturb under geometric optics condition, I can perturb with A of x phi, because this A of x phi will be in high frequencies will be eaten, although it is not compact, because that's a big difficulty, it's not a compact perturbation, but it's still small in high frequencies, and due to the fact that capital M goes to 0, we can eat this this perturbation in high frequencies. So here here will be, but even here that is not completely solved. In fact, it is clear. Then it's AA and A of x is real. So the proofs which no, here I don't need this. Sorry, here I don't need this. But this is the case in the situation of, as I mentioned, adding this A of x has been done by Burke and Zworsky, also for the rectangle with sorry, L infinity or L. I take it L infinity. The best results which are available are with A in L1, I think, or L2. The result, yeah. But so with geometric optic condition, it's an easy proof with A in L infinity. Without geometric optic condition in the rectangle, Burke and Zworsky need A to be like L2, but they need it to be purely imaginary. That's a bit. They say that it's not probably essential, but it has to be written. So why purely imaginary this perturbation? Because they want the operator to still be skew adjoint. If you add an A of x which is real, for instance, you lose the skew adjoint character of the problem, which is a difficulty in the spectral decompositions and so on. But okay, but this is not a problem in our simple situation where we assume geometric optics. Okay, now what about the plates? So here again, I will write the plates in an abstract setting. So H and Y Hilbert spaces. A0 will be a strictly positive operator. A0 will be minus Laplacian if you want to think of the plates. And I introduce the scale of spaces H alpha, which is the domain of A0 alpha endowed with the graph norm of A0 alpha. Then A0 can be, as I mentioned, restricted as extended to a unitary operator from H alpha to H alpha minus 1. So no, it not be unitary. Why should it be? From H alpha to H alpha minus 1, yes, it is unitary. And I take an observation operator bounded here. Here I need it to be bounded. And the problem I will be interested in, if I write it in a more understandable way, it's W double dot. So the plate equation will be with A0 squared. That's why I choose those boundary conditions, is equal to 0. So that's my differential equation. And my observation, where is my observation operator? Will be the output will be CW, I think. Yeah, let me check if it's C0W. So that's my observation problem. And which writes in first order form with this curly A operator and with this C observation operator. Okay, and then this is the operator I'm interested in. What I assume that the wave, which is this A tilde, here I have just A0, not A0 squared, wave tilde, the wave with the observation operator, which is the same, with the same observation operator C, I assume that this is exactly observable. So the theorem says, if A tilde is exactly with the same observation operator C is exactly observable, then AC is exactly observable in arbitrarily small time. And strongly than that, I have this Hautus condition. I have this Hautus condition with an M1 of omega, which goes to 0 when omega goes to infinity. So here, we are all the time in the framework of skew adjoint system. I don't have yet any perturbation. And this is done by playing quite a lot between the usual Hautus test and the spectral test I have shown you, but it's a simple functional analytic proof at the end, exactly in the setting I showed you. So for the plate equation, the novelty in this result is that my Hautus test holds with an M1 of omega going to 0 when omega goes to infinity. And this allows me immediately to do linear perturbation. So here I add a perturbation which is second order. So because what is H1? H1 is the domain of A0, which is a Laplacian. So H index 1 will be the Sobolev space H2. And H will be L2. So this is a second order operator potentially. I ask him also to go, roughly speaking, from H1 0 to H minus 1. This is not automatic in an abstract setting. And by perturbing, by adding, so what I will do, adding here P0W, under the assumptions which are here, the new system is still exactly observable in the same time as the original one. In arbitrarily small time. No? Because my assumption is, again, that the wave is observable. So which are the assumptions on the perturbation? So it has to be second order. It has to satisfy a symmetry condition as an operator from H1 from H to H minus 1, for instance. It is the same thing. And also to satisfy this condition, this Hautus condition, again, which in fact prevents us of having eigenvectors which are not observable. Okay, then I have the perturbed system exactly observable in any time. Again, the proof, it's quite a simple consequence of the fact that this M1 of omega for the unperturbed problem goes to 0. The difficult part here is just that our operator perturbed one will no longer be written in as a first order system with skew adjoint generator. I lose the skew adjoint character of the first order problem, but we are not so far of it. We can recover some of its features by a careful spectral analysis. Now, which will be the application to the plates? I want to take perturbation like this. H1 is the Sobolev space H2, W22. So here. And of course, it's bounded if I take it second order with AKL in L infinity. And what I need, my unique continuation would be, I have this condition equal to 0. It's an elliptic problem. I have the boundary condition, and phi is equal to 0 in an open set. Then it's not completely obvious why is phi is equal to 0 here. And in fact, what we use, it's 2 times the Carleman estimates for the Laplacian. Because Carleman estimates for the B-Laplacian are quite ugly. If we can avoid them, we are very happy. And here we can, again, because of this nice boundary condition, I can do twice Carleman for the Laplacian. So in P0, why it is not, I cannot use, for example, analyticity, no? Because AKL are just an infinity. And finally, I will go to the von Karman system. So I will linearize it around the state eta, around the stationary state eta. And doing this, the difference between the exact solution and eta at the first order will be delta, which satisfies this linear equation. So here, again, you have the formulas which are complicated for Q0. We have also the formula for the bracket. But what I see here what I have. In this bracket, for instance, I will have second derivatives of delta. That's how I define the bracket, with second derivatives. And second derivatives of this quantity, which depends on the stationary solution eta. Here, eta will appear in a more, delta will appear in a more complicated manner. So in fact, the problem is to show that this one is exactly controllable. Then we can apply a fixed point with care and obtain our local nonlinear controllability result. So here we can check that in fact all the assumptions are satisfied. The problem will be the unique continuation. For the unique continuation, or for the observability of eigenvectors, here we need to assume that eta is analytic. So the stationary state around which we are linearizing here is supposed analytic, and then we use some analytic continuation arguments to obtain our observability of eigenvectors result. Clearly, this is not sharp, but we suspect that eta cannot be arbitrary in a Sobolev space also. So you see, these terms are quite complicated. It's not local. I can do it local by adding the second equation, which is elliptic, but it will become a system, and it's far of being obvious in this case. So this is for the von Karman system, and I think that should be the end of my talk, or almost. So as I mentioned, for Schrödinger, what would be interesting is, without geometric optics condition, to add arbitrary perturbation of order 0. Doesn't seem so difficult, but because many things have been done. Adapt the theory we have developed for plates in the case where omega is a rectangle and O is arbitrary. Our theory for plates allow capital omega arbitrary, but O needs to satisfy geometric optics condition. Then to relax the assumptions on the state eta around which we linearize in von Karman. Also, I don't know if there is an application, but to enlarge the class of second order perturbation which work for plates, the fact that we use this symmetry is in fact somehow the counterpart of the skewed jointness for Schrödinger, the perturbation for Schrödinger. It's not exactly the same, but it's in the same spirit, and it should probably be relaxed. And then we can also look, so the von Karman system has a very nice application. It is used to describe buckling of nonlinear plates. So what is buckling? If you have even a beam, because I can easier draw a beam, and if I compress it from both ends, from a certain compression force, the solution, of course, which is just contracting the beam, is there, But a second solution can appear called the buckled one. And then, but the system is essentially the von Carleman system coupled with another system for the in-plane movement. And then I can try to control this system around, for instance, such a state, which should be not out of reach, since the classical von Carleman system, we are able to control it around any stationary state. But here the system will be slightly more complicated. So I think that that's all what I had to say today. I'm, of course, open to questions. Belasen. Go.
Marius, please, when you spoke about wave packets. The wave packets.
Yeah.
Can we see the slide?
Yeah, it's like quite at the beginning. Here.
Right. I'm not sure. I didn't see that there is sufficient condition. If you have observability on each wave packet with a constant which is independent of the wave packet, you have global classical observation.
That's what I say. It's equivalent to the fact that AC is exactly observable. The fact that I have observability of all the wave packages, this is condition S1.
Your wave packets are indexed by R, something like this. See, you have...
R is the size of the wave.
Yes. Okay, it's fixed.
Huh?
It's fixed. Surely I understand wrong, but in my mind you have a spectra which is countable.
Is
countable.
Yeah.
Lambda k, go in. Okay, so the wave packet are adjusted on the lambda k. And the size, your size, which is fixed,
centered in omega. So you can have in one package you can have very many eigenfunctions.
Sure.
So even in the case I considered here, so how many I have? So it's not all the same thing. So how many can I have on the circle? So how many points Mn satisfy M2 plus N2 is equal to R2? There can be a lot. The number of M and N we satisfy exactly this when R goes to infinity. Just on the disk. On the circle. And if you want to take several circles, it will not work. So here
what I don't understand, excuse me, well, we can discuss later, but I don't see any advantage to prove observability on each wave packet since the packet doesn't move. I mean, it doesn't move with K.
Omega is moves, but omega is moves.
No, you fix omega and you just see the new K that are in this.
But there's nothing, I have to have something independent of omega. So I have a wave package. So for instance, if I have a first omega here, I may have one eigenvalue or nothing, and omega much farther, and my wave package, here I will have a lot. And in fact, it's only these ones which are interesting for me. Omega large.
I followed the book, I tried to understand really. It didn't succeed. Surely I missed something. No.
Well, we can talk. Yeah.
Sure.
Yeah.
Yes, thank you. Yes, it's not really a question, but a remark actually about the proof that you gave for obtaining the observability of Schrödinger equation on the rectangle starting from Zygmunt. Yes, so because I didn't know this proof, what is really interesting is the fact that in the series of paper of Burke, Bourgain, and Zworsky, they actually start also from a Zygmunt inequality, that it is completely different from the one that you presented.
Not the same. Yeah.
Yes, exactly not the same, but it's really the starting point, and they cannot do something if they do not have this Zygmunt inequality. And so just to mention the influence of Zygmunt on this problem.
Yeah, it's very astonishing, yes.
Yes, it's really astonishing, yes. Right.
Yeah, but this is just a classroom exercise, no? What I should.
Yeah, yes. But do you have a reference where the proof of the observability inequality is done like this, starting from Zygmunt?
Where?
Do you know an exact reference where the observability inequality for Schrödinger on the rectangle is done starting from Zygmunt? No.
No. The proof of Jafar
Yes.
is based on the theory of lacunary series developed by Kahn.
Okay.
This we redo it in the book. And then there are the proofs on the boundary case which I gave with Tenenbaum, which use again the Kahn theory, Kahn-Berling theory, and a lot of arithmetics.
Okay.
That's how we do it.
Okay.
But then I think I'm not sure what happened in the meantime with Burke's work and so on. But they don't look too often to the boundary case. Okay. Because microlocal defect measures on the boundary it's a more complicated object.
Okay, thank you.
Maity. About yes.
So you didn't use it for bi-Laplacian, but you used it for
Yes, but I use it twice.
for Laplacian.
For the for the Laplacian twice. Here. For the B-Laplacian, I don't have something. I don't have a Carleman estimate for an orbit, a global one for an arbitrary. So let me go here. So why is simpler to pass by the Laplacian? Because here I know that phi is equal to 0 in O, and O is anything. Could be anything. If O is anything, then it's difficult to do Carleman estimates directly on here. So in fact, I first give an estimate. I write this Laplacian phi. I treat this as a source term, and we do a Carleman estimate for the Laplace, which is known. I just write it, and then I use or more clearly, I can express bound phi in terms of Laplacian phi and its trace on O. That's a first Carleman estimate. And then I insert it here and I apply it again, because here I have Laplacian of Laplacian phi. I apply, it's applied just twice. It's very easy, it's not a difficult result. It makes it much simpler than, I don't know, it certainly exists. I think in the thesis of a recent student of Le Rousseau, there is only this, a lot of plate equations with various boundary conditions where they have Carleman estimates, and it can be obtained, but it's much more complicated. Okay? Yes, yes. I take advantage of the boundary condition. Yes. Yes. Provided that the observation operator is well chosen. Yes. We have also results in this direction. So for plates with boundary observability, I can obtain that boundary observability holds from corresponding properties of the wave. In fact, the simplest way is to pass by Schrödinger. From Schrödinger, I get automatically plate. So from wave, I get Schrödinger, and for Schrödinger, I get plate. That's sorry?
Boundary or
yes.
the properties.
Yes, yes. I don't need the operators to be bounded, but always with this W is equal to Laplacian W is equal to 0 on the boundary. Otherwise, passing to plates, it's extremely complicated. It's funny. In fact, we don't know for a very basic problem, this plus B Laplacian W is equal to 0. And I put here, for instance, W on the boundary is equal to U, dW over d nu on the boundary is equal to 0. Or vice versa. Let us take vice versa, the opposite. We don't know necessary and sufficient conditions for controllability of this one. The part of, not on the all the boundary, on a part here, this on the whole, and this is just on a part of the boundary. We know nothing, or even with internal control. Let me take it even simpler, sorry. I take here U times an internal control. We don't know necessarily sufficient conditions for O to have controllability. There are some results which are very old now of Zoazua, which say that if the Lyon's condition holds, then it works. But that's all. So this operator requires a special study. Even in 1D, the eigenfunctions of this one are very ugly. They form a basis, but it's a combination of sine hyperbolic. You cannot manipulate them. Of course, in 1D, we are able to do them. Even with these ugly boundary conditions, we can do it. But in 2D, the only result I know is Zoazua, which dates for a certain time, and it has this very strong assumption.
Any other question? From online? If not, let's thanks Marius.
Thank you.